encapsulation material so that you can actually characterize the volume of the channel rather than just looking at the bottom surface. 3D microscopes can also be used to quantify film thickness, and that can be anything from quantifying photoresist, which is really important, particularly in etch processes. If you need to know the etch rate, you can pull parts out, characterize the photoresist thickness, very precisely dial in the etch rate. You can look at the thickness of polysilicon. Inherently, it becomes opaque only really as you go into the blue and green regimes, and so 3D microscopes can look and characterize polysilicon thickness, and you can also look at protective coatings that are used to reduce friction or wear or other properties. So essentially what happens in a microscope is every interface creates a reflection. So you get a reflection from the air film interface, and you get a reflection from the film substrate interface. And as long as those interfaces are separated by about 1.5 microns, it can be a little lower for some materials, all the way up to 600 microns, we can analyze those two signals separately and do characterization of the top surface roughness, top surface shape, bottom surface characterization, as well as look at overall film thickness. And then there's also specialized objectives that are available, again, to support measurement through very thick materials. For instance, into environmental chambers or through thick encapsulation. So on the upper left, we see, what would the signal, and again, these bright and dark bands you kind of see washed out on the upper left and more firmly on the upper right. Those are really the signal that's being used to do the characterization. So with specialized objectives, you can go from very weak signal looking through encapsulation to have a very strong signal that, again, can give you very precise characterization of mirror arrays. In this case, this mirror is courtesy of Sandia National Labs. Also, very recently, there's been advanced techniques introduced in 3D optical microscopes that significantly enhance their lateral resolution. So just a few years back, people would say the lateral resolution limit of a typical optical microscope resides somewhere around 1/2 micron, 500 nanometers. But with new techniques that involve modeling and multiple measurements, we have a patented technique called Acuity XR. You can actually significantly enhance the lateral resolution of your measurements. So here I've zoomed in on a 10x measurement of the edge of a microgear. And on the left, you can see there's some pixelation, some loss of resolution. And on the right, it's the same exact part using the same exact objective and camera, and we get a significant enhancement in the lateral capabilities of the instrument. What that translates to is we've actually seen more than a 3x gain in gauge capability on things like widths, heights, areas, and volumes using this technique. And it actually allows us to image structures all the way down to 130 nanometers wide. And, that's more than a 3x improvement over anything that used to be specified in the literature. But really, one of the unique characteristics of MEMS devices is that static measurements are not enough. So it's great for quantifying the surface. It's good for figuring out if there's defects or if there's gross problems, but it doesn't really tell you how a MEMS device is going to perform in practice. For that, you really need to measure the device dynamically. And dynamic measurements, they quantify the true device functionality. And micro-device operating failure modes differ significantly from the non-operating failure modes. And by that, we mean, what's going on in terms of wear, in terms of asymmetry of motion, and other things. So if you look at the video on the lower right, again, this is a resonator that came to us from Sandia. If you just look at the center circle, we would like this device, it's being driven by a symmetric voltage signal, so we'd expect symmetric motion around the center. You can see it moves way more to the left than it does to the right. And that means that depending on how this device is oriented, it's actually going to perform differently as a sensor in one orientation versus the other. For instance, if this were an airbag sensor trying to look at deceleration, one way versus the other, you're going to get a stronger signal. And so you need to really characterize the moving structure. So you look at shapes, distortions during motion, radius of curvature, sag, bow, deflection. What is the range of motion? What is the rise time? What is the settling time? And then you can also characterize the resonant frequencies of the devices very precisely using dynamic techniques. So you need to be able to do both in and out of plane motion. You need to be able to look at both static and dynamic. So how do we actually do dynamic measurements using a microscope? Well, the technique is fairly simple in principle, a little more complex in practice, but it's via strobing. So if you look at the diagram on the bottom, our camera, in terms of the MEMS devices, which are typically, they'll have resonance frequencies in the kilohertz range, maybe even in the megahertz range. But the camera typically is, they're integrating a 30th of a second, things like that. So it looks at light over a very long period of time. The MEMS device over that camera frame is going to move a lot of cycles. But if I have my light source that is precisely synchronized with the MEMS motion, and I strobe it, it essentially freezes the motion with respect to the camera. The camera only sees the device, in this instance, at the bottom of its cycle. And if I then move that strobe to a different relative phase with respect to the MEMS device, I see the motion at a different point. And so I can build up a dynamic picture of what the device is doing. And I can look at different frequencies, different voltages, different drive signals. And all of that looks frozen with respect to the camera, so I get the same high-quality results, but I can actually measure things up to 2 megahertz frequencies. One thing I did want to just briefly mention is that MEMS devices often require additional hardware that should be considered when you're looking at metrology. What is the capability in terms of being able to handle the additional hardware, and is it sufficient? So it's easiest to test devices using ZIF sockets, so that's usually an important thing. The actual mounting of MEMS devices is extremely important for good characterization. So they're small devices, they are fragile devices. One of my favorite experiences was when one of our product managers accidentally sneezed onto a micromirror array, creating essentially micromirror confetti in the lab. But so you need to be able to fixture these, you need to be able to protect them. A lot of times you're going to want a vacuum fixture, but because MEMS have so many different characteristics, so many different sizes, you want something flexible like a porous ceramic chuck so that I can kind of put any size device on there, hold it very securely and safely, and do nanometer level metrology. And then also being able to handle probe platters. So you can use magnetic probes or vacuum probes, but in order to actuate the device, you need to provide drive signal to it. And so making sure you have the real estate to do all of that is important. And for instance, we have a line of 33 millimeter working distance objectives that were primarily designed, just to give people that additional access so that their part can be, well removed from the metrology head. And as you do dynamic measurements, you can actually see and measure coupled 3D motion. So in this particular case, on the left, I have a measurement where I've subtracted 2 results. So I've looked at the MEMS device at 2 different points in time, and I've subtracted them, and it's false color where red is high and blue is low. And you can see the device in the 3D image on the right, it's tilted. It's been twisted as it's actuated. And so something's going on. And so in the center, we can actually break the device into a whole bunch of different subcomponents, characterize each of those subcomponents, and really very accurately get down to what is going on in terms of tilts and translations of each subcomponent and see if we can find the problem area. And then I've already shown you guys some of the 3D animation, but being able to take your measurement sequences and put them together into an overall movie is often very instructive. So, here we have a micro gear array rotating, and a lot of times it's very instructive to see,